Thank you so much for the introduction, and thank you so much for the invitation. It's truly my honor to attend this great conferences. I learned from experts and friends, and it's also impressive to see the outstanding young students. So for this purpose, I revise my slides so that to for for the beginners. So I hope you can benefit from this. So um, first of all, this talk is based on the groundwork with prophecy. So I start from motivation and state some conjecture and also some result. So to begin with, let me remind you from the basic complex analysis. So as you students learn from complex analysis, we have the Cauchy integral formula. So we deduce the real theorem, which ensures that on the complex plane, you cannot have non-constant bounded holomorphic function. This is the real theorem. And on the other hand, the unit open disk D contains lots of bounded holomorphic functions. This is the second fact is pretty trivial. We just restrict the holomorphic function on D. On the other hand, by Riemann mapping theorem, any simply connected domain on C, as long as it's not the whole C, it's biholomorphic to D, then the second fact means that those simply connected domain, not C, also admits bounded holomorphic functions. So it's less trivial by these Riemann. Okay. This is from analysis point of view. So let's look at geometry point of view. So the C, on the other hand, has no metric with curvature, Gauss curvature bounded away from zero, negative curvature bounded away from zero. And this D has a metric. It has such a metric, negative metric bounded away from zero. Again, the first fact is not so trivial because C can admit a metric with negative curvature, that's just close to zero. And also C can admit a metric with positive curvature. You can just restrict Fourier student metric to C. So the key is that C cannot have a metric which is negative and bounded away from zero. So this is the geometric fact corresponding to this and this. So in high dimensions, we now we look at several complex rows with high dimensions. They also look at functions on complex manifold. But what if the manifold is compact complex manifold? Then unfortunately, by the maximum modulus principle, you know that there's no non-constant holomorphic function on the compact complex manifold. So what we do, so the answer is let's consider holomorphic sections of canonical. Canonical bundle has already introduced in the Professor Peter Nell's talk. So here I probably do the prehistory. So Andrew Wei mentioned that we should consider holomorphic section of this canonical bundle. This actually was a big deal because in the 19th century complex analysis, they all focus on domains on C. So these ideas lift this to a new level. So again, as Professor Peter already mentioned, so Km is a line number because the determinant of this K actually produce. So sometimes identified by name speed. So it's that. So it's top batch product. So it's rank one line bundle. It's not trivial because you have such a transition. But this is simplest. If you look at tangent bundle, the transition will be a matrix value. But here is a scalar value. The sections are just those Fc times Dz, one batch Dz, and F is a holomorphic function. So this is a generalization because if you look at Cn, any holomorphic function, you just times those functions with these top n form, you get a section. But in that case, in Cn case, the canonical bundle is trivial. So this is good generalization. And similarly, you can consider tensor product. Right? The tensor product of line bundle is still line bundle. So its transition function is just scalar and power. And the sections is locally given in this form. So we replace holomorphic function by holomorphic sections of these line bundles. So now the question now becomes, so when does Km or n multiple Km have lots of holomorphic sections? So Peter and I already mentioned, right, some condition like big. But here I just do the prehistory. So let's look at some examples. Well, first example is the CP1, the simplest one. The CP1 has unfortunately no non-zero holomorphic sections, because certainly this follows from the vanishing theorem, but we can do a hands-on proof. But we don't need to use big things, right? So CPN has a holomorphic sections, non-zero. So since it's global sections, so they should coincide with the on the overlap, right? So you remove the north pole, you get a chart. You remove south pole, you get another chart. So they should be agree on this overlap, right? Here the transition is that this W is equal to 1 over Z, right? So since they agree, you use these. Right, so then this is equal to this should be G, right? different function. Different chart, different functions. But they agree. So they agree means that FC should equal to minus G 1 over Z squared. Right. Or Z is not equal to 0. You should agree. But since they are holomorphic, like they're holomorphic on C and C, so you can take a Taylor expansion. So you write this for F, it should equal to for G. You get this too. Should equal. Now you compare the orders, you can prove that this AN is equal to BN is. So F G is equal to C. So you only have 0 sections, right? So this is the elementary proof. One doesn't. So when Km and Km lots of sections, the one answer is classical Kodaira theorem. Right? If Km is positive, this is stronger than that introduced in Peter-Nels talk. Right? It's positive. And positive means that you can find a Hermitian metric on Km such that the curvature form minus dd bar log of this h is strictly greater than 0. Right? In this case, then you can have lots of plenty of sections. So clearly, this KCP1 is not positive. Actually, it's minus KCP1 is positive. Remember Kodaira's theorem is about metric on the line boundary. Right? Now the question is, can you use geometric data on these on the manifold itself rather than the line boundary characteristic? Right? So we're going to use some curvature on the manifold. So we use Chen's result. First Chen class of canonical bundle can actually be represented by dd by log determinant GRG. So this is actually minus negative Ricci curvature. So if you want this guy to be positive, then you need to have a metric whose Ricci curvature is negative. So by Yavanovani solution of Calabi conjecture, so actually M admits K-lines metric Ricci curvature is 1. Then if this 2, then this will be positive. So the criterion is that if M admits a K-line symmetric Ricci curvature minus 1, then this guy is positive, then Kn is positive. Right. So the one characterization is the Ricci curvature. If you have a negative Ricci curvature, then Kn is positive. All right. Is that right? The Ricci is the question is, do you have other criteria for Kn positive? Another viewpoint is now we look at holomorphic maps. Right. Holomorphic map between complex manifolds. So a compact manifold M is called Kobayashi hyperbolic if any holomorphic map from C to M is constant. So this definition actually equivalent basically says that the manifold we're going to have a Kobayashi metric. If you have a Kobayashi metric, then you can have such a non-constant in this map, because Kobayashi metric you need to have a positive lower bound for the one of the radius of the disk. The disk needs to have an upper bound. Anyway, so this definition is clear. So it's equivalent to this Kobayashi metric. So we take this as definition. Also favor for the geometry. Now the conjecture of Lang and Kobayashi is that, okay, so if a Kn manifold, if it's hyperbolic, then Kn should be positive. That's the conjecture. So far still open. Lang the original conjecture of Lang is about projective case, and Kobayashi extends conjecture to K. Even for projective case, it's still not. The next criterion will be, let's look at holomorphic sectional curvature. So what is holomorphic sectional curvature? Well, this is a natural generalization of Gauss curvature. Right? So geometrically, okay, you have a complex manifold. Say holomorphic sectional curvature at a point around the direction tangent vector means that for this point as tangent vector, you take a curve, complex curve. Take a complex curve, it's a Riemann surface, right? You look at its Gauss curvature. It has a Gauss curvature. But you can have different curves paired to point with the same tangent vector. You have different Gauss curvature. Now you take supremum of all these Gauss curvature. Then you define this supremum to be a holomorphic sectional curvature at this point of curvature. So that's what it is. We define this way, this coincides with the standard way to define this is that is due to the decreasing property of holomorphic sectional curvature for submanifold. Submanifold is always smaller because second polynomial form has a sign. And it's ambiguous defined because for Hermitian metric, right? So in general, the Ricci curvature you cannot swap the indices. So Ricci curvature you have 3 to 4 cases, right? So that's scalar curvature 2 cases. Morphic sectional curvature is unambiguous. Now the conjecture is that for compact complex manifold, has negative holomorphic second curvature, then canonical bundle should be N. That's Gauss conjecture. And certainly, again, the previous one is about projective case, then he's the extent to Taylor, then what about general complex? So we have two conjectures, right? Two different. One is from map of holomorphic maps, so called hyperbolicity. Hyperbolicity implies K and positive. The other is about holomorphic section curvature. Holomorphic section curvature is weaker than Ricci, right? Because Ricci is the trace. Holomorphic section just you do each guy has a sum, but the Ricci you require trace. So negative holomorphic section curvature does not directly imply negative Ricci. Right? So to me, it's not very evident why these conjectures are true. But let's look at the relations of these two conjectures. Right? So the relation is connected by Schwarz lambda. It's basically a talk about maps from between complex manifolds M and N. Right? So here you pull back metric on the target back to the domain, then they should be related by these inequalities. This lambda n and kappa n are lambda n are sort of curvatures of the metric on M, and kappa n is the bound of curvatures of omega. So biholomorphic. Holomorphic sectional curvature. No. Oh, bisectional curvature. That's true. Bisectional curvature is good. Yeah, bisectional curvature means you have two. Right. Certainly, bisection for any ij, if this is less than or equal to 0, then it implies this guy less than or equal to. Right. Bisectional curvature is stronger than Ricci, but holomorphics, Yeah, all the holomorphics. That's right. Now, classical Schwarz lemma is, remember, your complex analysis class, right? So it says that you have a map from C to C, then the origin to the origin, right? Then F prime at 0, the norm prime 0 is less than or equal to 1. Right? This is the classical Schwarz lemma. Certainly, you have other equality case, but here let's just. So this is equivalent to saying that you pull back the boundary metric, right? So less than or equal. This is a formulation of Schwarz. So in this case, basically from D, take boundary metric, your negative curvature bounds at 1. So alpha is generalize this to from D to Riemann surface. But Riemann surface need to have negative curvature. And then extend that to map between Hermitian manifolds of equal dimension. Right. Then it's Gauss version of Schwarz lemma. Right. Gauss version of Schwarz lemma remains to be the most influential one, because that relax the dimensions, right? And can be different dimensions. It has a Taylor, but need to be complete. And it's Hermitian. So here, for the domain, you need to have Ricci, need to have lower bound. For the target, the bisectional curvature have a minus upper. So here, this need to be negative, and this doesn't need. Well, this is bound, right? This need to get negative upper. Here, bisectional curvature Hermitian metric basically is this form, the first bisectional. So once you have this, then you can get this Schwarz lemma. That's Gauss Schwarz. This remains the most influential one, because in this paper he also apply his general maximum principle. So this is powerful tool. But in our talk here, we just talk about compact manifold, so we don't need to use that powerful tool. And then Lorentz has an alternate version. Lorentz version is that you look at the target, now it's scalar. Target is also scalar. In this case, Lorentz uses average check to replace bisection curvature to be holomorphic section. So that there are many other results. So just focus on this classical. Then by Yau's-Schwarz lemma, if you have a complete, actually in this case you can do Hermitian. Then any C to M's Hermitian will be fine because it's one-dimensional case. Bisection curvature is just IC equal to J. So any map holomorphic from C to M has to be constant, right? Because by this inequality, right? C, you take the standard metric, the reach lower bound will be 0 because the standard metric has curvature identically equal to 0, right? So your pullback will be 0 if it's not constant, right? So every holomorphic from C to M is constant. All right. So that means if a compact manifold is compact, has negative holomorphic sectional curvature, then it must be hyperbolic. So the relation now is that it's hyperbolic. So this is Lang and Kobayashi conjecture, and this Gauss conjecture is holomorphic sectional curvature is equal to 0. So the Schwarz lemma basically says the following: if this is true, then it's hyperbolic. So this Gauss conjecture is weaker than Lang and Kobayashi in the case of Taylor case. This is true. Yau asks conjecture for general complex. So this is weak. Anyway, so despite this, there was no much evidence why this is true because curvature condition too weak. So let me mention some results. So that it will be incomplete list. When n equal to 2, complex dimension equal to 2, you can use classification of complex surfaces. It's already mentioned in Damin's talk, right? So you dimension 2, say, remember you can have say P2, CP2, or CP1 bundle over a curve, but these cannot be hyperbolic because by Schwarz lemma, there's no C map from C to M, so you cannot have rational curve. You cannot have elliptic curve also, because if you have an elliptic curve, you can go to C cover different. So by classification of these, so you can prove these Gauss conjecture and Lang Kobayashi. N equal to 3 is Professor Peterson. It's 30 years ago, probably out of date. So now you can do it probably for Taylor threefold problem. So Professor Peterson also showed this Lang conjecture. It remains possible for some Caviar threefold. There's no rational curve, but not sure they are. They could be there because they are not. They don't have positive canonical bundle. I'm not sure it can be a hyperbolic. This is the open. I see. And that's a really good, interesting thing. And more than 10 years ago, I'm joined with Pittman and Professor Yao. we still have no idea. So what we do is that we pose a condition, Picard group equal to Picard group rank 1, so that things are simpler, because this we do for Yau's conjecture. Yau's conjecture says that holomorphic section curvature is negative. So we already have a metric whose holomorphic section curvature is negative. Right? If rank is 1, then we can connect this to a metric with which curvature has a bound. Then we apply Schwarz lemma to get some information. Right? So we can show that the Ricci has to be negative. If Ricci is not negative, we're going to use Schwarz lemma to get a contradiction. This we use this to pick up group 1 information. But other than that, we don't much focus. Then we have this higher Wu Wang's paper. So this, in my view, is very enlightening, inspiring. So they prove Gauss conjecture by assuming the abundance conjecture. So at least they convinced me that at least Professor Yao's conjecture should be true. And of course, Yao's always confident with his own conjecture. So, all right. So what's the argument? Well, if holomorphic section curvature is less than 0, then by Schwarz lemma, any C2M is constant. So what I mentioned. Then M contains no rational curve. M is projected for the moment. Yeah, for the project. So this one coming from Kohn theorem or Morris theorem, as mentioned in previously. So if it contains rational curve, if it's not, then so contains no rational curve implies Km is net. Net already mentioned in Peter Nell's talk. So here I'm just mentioned net. We can just understand Km is greater or equal to minus x for any small x. Now here's the abundance conjecture come to their picture. Abundance conjecture asserts that if, to my knowledge, Kodaira dimension is equal to the numerical dimension, equal to n. And higher Wu Wang, they showed that they use the so-called Neff induction, maybe also same trick mentioned in Peter Nell's talk. They show that in that case, Neff m is equal to these 3. So they are equal, and because abundance conjecture asserts that these are all equal to, they show these equal to n, so all these equality holds. So all these equality holds, then that means Km is big, right? It means you already have lots of sections. So by algebraic geometry, also Peter Nell's talk, if it's big enough, no rational curve, you can show that projective case it's exactly. That's the argument. So here the first step, the first few steps to here now is no problem, and from big to here is also good. So the only thing is the unknown was abundance conjecture, as in Peter Nell's talk. Abundance conjecture so far I still know for 2-dimension 3 and maybe some other cases, high dimension, separate isolate cases. So at least they prove Gauss conjecture for dimension 3 and other cases, right? But still, caveat repos is that maybe they do in this step. They maybe because they use abundance conjecture and they show this equal, and then this go through. Calabi Yao trivial. So maybe that's not because the depth dimension in that case probably not equal. Maybe in that case, I don't know their proof for this detail. Yeah. But maybe they overcome in this case, but which is good, right? Because I don't know the step. So when I read a paper, I don't know the step. I have to think about a way to bypass this. So we have Right, that's a good question. So I don't know how they overcome. So, but what we do is that from here to here we bypass the abundance conjecture. So we go from here to here. We don't use that. So what we do is that we are familiar with this Schwarz lemma, right? So bypass use among geometric equation techniques and Schwarz lemma. So we show this conform Gauss conjecture projective case, and because of decreasing property, we also obtain the result that every subvariety of this manifold, the canonical bundle is also negative, because of the submanifold, the holomorphic section closure is also negative by decreasing. So our proof is the following. Because inspired by their result, you just need to show Km is big, actually. Right? Km is big can be reformulated as the volume of this basically this interval, like volume interval is constant. You just need to do this. Then the nakedness, remember nakedness is that this canonical bundle has a metric is greater than minus epsilon omega. Right? You move that to this side, you get positive one form, smooth for epsilon greater than 0. Then we can solve a Monge equation to get this u just u epsilon. Right? We can solve Monge equation for get this u epsilon with this thing. This equation, well, unlike the Calabi equation, because here we're talking about Km positive. So, but this equation has a nice feature that if you take Ricci curvature, it's equal to this one. This is very straightforward to see because right, this is the Monge equation. So what about what's Ricci curvature? It's a DDC law. So this will be a DDC of u epsilon plus DDC log of omega to the n, right? And now you replace this DDC u epsilon and this log here by omega epsilon minus this. So this is equal to epsilon omega. So omega epsilon minus epsilon. Right. So what is Ricci curvature? Ricci curvature is minus side of this. So Ricci is minus side of it. So you take minus side. So that's a relation. So what's the good for this? Well, this means for this family, the Ricci curvature has a lower bound. Right? In general, the Ricci curvature can have a infinite minus infinite, but this one has a lower bound. So once you have lower bound, then you can apply Schwarz. Remember in Gauss Schwarz lemma, Gauss avoidance Schwarz lemma, you need to Ricci curvature have lower bound. And holomorphic section will already have. Right, so we use Schwarz lemma, then we get this nice this helpful estimate. So we summarize this into a Schwarz lemma. This is a little different from Gauss classical Schwarz lemma in that here I don't look at maps. In other words, I use the identity map. So we have two metrics now. Now background and target, we don't distinguish. Right? One metric Ricci has a lower bound like this. The other metric, these holomorphic section curvature has upper. Now you do calculation, you get these inequality. Here lambda is the lower bound of this Ricci respect to itself, and mu is the bound respect to omega 2. This is still useful. But you know. So why is it useful? Well, now it's a compact manifold, right? So now you can apply maximum principle. But by maximum principle, you get less. Actually, you get lower the action term in this case. Just get this. This is a fixed bound. This because it's bound. Now from here we can get a volume bound because we just do elementary inequality, right? Elementary arithmetic geometric inequality. Then from here you get this is choice arithmetic average, right? This is determinant choice greater than determinant. So from here you easy to get this bound. From this bound, from this bound you just multiply both omega n and do integration. Then so it's proof. So it's method one, right? Remember you want to get this bound. So use non-general equation minus this. But here here we use the characterization of the bigness. Actually, after we obtain this bound, we know that actually we can get more. We can get pointwise estimate for the non-general equation. So indeed, as before, we already get this trace bound. Now you look at this non-general equation, and the right hand side is very special. Right? This is the negative curvature case. You can take maximum principle directly get strip bound for C0. So you have C0 bound, you have second order bound, so you're going to get these traditional hypotheses. So actually you get uniform bound for second order derivative. Right? This is much easier than the second order causes. So this one is because the geometry plays a role. So once you have this, then it's a second proof. So in general, if you have two proofs of your result, then your result is very likely to be correct. So yeah, so so this is a projected case. So after we done, so Valentino and Xiaokui, these are smart people. So they look at, they quickly generalize. They notice that in our argument, so the Schwarz lemma here, if kappa is just semi-positive, say if it's 0, it's still fine. Actually, you get to here. Well, S would depend on epsilon. The upper bound depends on epsilon. But for netness, you don't worry about netness. Just epsilon is always there. So this is already good enough to handle the net case. So they prove that if h is less than or equal to km is net. Remember we use Morris result, right? Net. Then we get the Monge equation. Now he actually used our Monge equation to directly get this net. So they extend from projective case to complicate. Very nice observation. So now it's true for K-element. When did you use projective? Yeah, projective, and actually we didn't. So projective case is this. So so we get this definiteness. So NF means that you can find a metric. You find a metric on this Km, say there exists say Fm, such that these epsilon plus EDC log omega n plus EDC F epsilon is greater than 0 for any epsilon. Right. So this is the NF used. Then from here we can solve this U epsilon, because what we do is that we look at this. Then we solve a Monge equation for V epsilon. Right, this is the background metric now. Solve this equal to e to the V epsilon plus F epsilon. F is given. Solve V. So once you solve V, now you set that U epsilon equal to F. But later on, I'm going to mention that actually we don't need this methods. We can bypass this by completely using non-geometric equation techniques. So I'm going to mention a few slides. For the moment, at least Valentino and Xiaohui, they show that actually curvature can get at that methods. And then, nice work is the Divirio Trapani. So they proved that actually this Yau's conjecture actually under a weak assumption that the holomorphic section curvature just need to be positive negative. Right? This actually we did in Pippen with Yau, but for the case we assume the group has rank 1, but we don't need that. So quasi negative means that H is less than or equal to 0 everywhere, but strictly less than 0 at one point. So again, you just need to show the volume response. Now this time, again, we use the Schwarzwälder method. Now this time, let's drop off this epsilon term so we get this. Now from here, you estimate this. So difficult part is that you worry about the volume shrink to 0. In other words, you worry about the maximum U, the solution U, maximum U will actually tend to minus infinity. Right? This sounds weird, but it can happen. Right? The volume totally collapses. We know maximum U has an upper bound, but it could go to minus infinity. So how to prevent that? You use these, now you do integration. But this time kappa is less than, kappa is greater or equal to 0. It's just only positive at one point. Right? So you keep it there. Now you get this in. Now you divide, now you renormalize in this term. Now you use the fact that like a subharmonic function, it has upper bound, then you get some weak convergence, the L1 or L2 convergence, then it converges everywhere. So that epsilon goes to 0. This term is actually under control because kappa at least has a 1 point positive. Right? So it won't go to 0. So use interval method to control this margin. So this will sufficient implies this. And of course, this is due to these D- holomorphic most important. So the D- schools really familiar with hypertechniques. All right. So this is the use of private algebraic geometry. So then Yao and I realized actually we can use a purely analytic approach. So what we do is now we consider replace epsilon by t. Right. This new long-term equation, this is basically the previous. Right? We just need to look at t go to 0, but we don't need methods. What we do is that we use continuity method. For continuity method, consists several components. Right? Openness is always true by the standard implicit function theory. Because it's basically just Laplace minus 1. It's invertible. Now the interesting thing is non-emptiness. Right? In the classical long-term equation, you set t equal to 0, you get a solution. But here we start with very large t. For very large t, this background matrix is positive. Right? So this is a basic new Taylor form. Plus this is just classical long-term equation. This time we can do. So we get non-empty for very large t. So we have a non-empty solution for t, for large t. Now for closeness, our previous Schwarzwälder maximum principle, you get S. Now let t not epsilon. When t goes to 0, you get a k line. So all this process we don't need that. But actually implicit has that because if the kappa, the holomorphic section curvature is only semi-negative, then you have a solution ut for every t. But the bound can close up when t goes to 0, okay, for that case. So actually, we also divide methods. But if you just look at Km positive, then you don't need methods. So this method extends to complete non-compact limit as long as you have solution. And also, quasi-negative case, you do similar trick, like a variant Japan. So it's just a very simple replay action. But here, to get this convergence is the variant Japan use Damin Wu's big convergence trick. So here we instead use Chen-Yau's gradient estimate. By gradient estimate, you get a gradient L2 bar. Then we apply just the standard relative field, and then we get L2 convergence. Once you get L2 convergence, you can guarantee this bar. So then slightly different from group. So also true for this quasi-negative. So certainly there are many further progresses. Again, this is incomplete list. And Xiaohui and Fang Yang, they consider furthermore, they look at Kähler manifold, but now look at some permission metric, not Kähler, permission metric, but with the real bisectional curvature. I use this to replace the holomorphic sectional curvature. This real bisectional curvature is basically the holomorphic sectional curvature plus some torsion term. So this condition is slightly stronger than holomorphic sectional curvature, but again, they prove all these. They prove Yau's conjecture all these. So they include our previous. And for singular case, there's also a Henry Granassia. He considered the singular case. I remember we showed that the every subvariety also has ample canonical form. So we show that for every now it's possible singular subvariety, now it's of general type, then Km is big, slightly weaker than possible, but it's big. So, but this because of singularity, to work on singular version. There are also flow methods. So remember, we use Mongeum equation. So there are corresponding flow parabolic version. So there are many people do parabolic version, Nomura, Brad Tong, and Pounds, and many other people. And more recently, Broad and Stanfield now work on the compact limit. Now it's Hermitian metric, but post condition very close is DD bar or omega is equal to, right? So they are inspired by finance and real bus. So these are, so you can see that there will be many future work. So stay tuned for the future development. Okay, so yeah, that's all for my talk. Thank you very much.
Questions, comments? So can you go to this slide where abundance conjecture was assumed?
Oh, yeah, sure. Yeah.
So in general, NF and the big for the canonical bundle implies semi-ample, right? But here you get ample. So what is the?
Yeah, because the projective case, there's no rational curve. Rational curve will be the obstruction to get ampleness. So this because of the curvature condition, you don't have rational curve. Right. So big nav, no rational curve. That's for projective case. Actually, for Kähler case also true because you get Km big, then as you mentioned, it's more Shearson. So yeah, it becomes a projective. More Shearson manifold, Kähler more Shearson becomes projective. So you all go back to projective.
Yeah.
Right. So yeah, good question. Yeah.
Thank you. Okay, more questions?
Yeah, that's a good question. So yeah, I'm still working on smooth case. Professor Yao, I think he's interested in some singular case. Say you have a manifold some singularity, but you have curvature a negative curvature away from the singularities, right? So what can you say about these positivity canonical ones? Yeah, I don't know. So yeah, maybe you can think about it. Basically, technically, right? So what I know is that if you have singular case, then these if you use analytic method, then you you need to look at this maximum principle. How does this maximum principle go through to the singularity? Right? If that works for singular case, then you can still get some control. Certainly, there are also algebra.
Okay, any other questions? Okay, if no, then let's thank the speaker again.